Today we're going to be learning about Newton's law of universal gravitation and also how weight changes depending on variations in gravity. What is gravity? Gravity is a weak force. All objects have it, and it depends on a few things. Newton's law of universal gravitation states that gravity is universal. Everything pulls on everything else in a way that involves only mass and distance. Those are the two factors that affect gravity. Mass affects gravity in that as mass increases, the force of gravity also increases. So for example, down here, if the distance between the centers of two objects are the same, if you were to increase the mass, the force of gravity, the force of attraction between the two objects would increase. Distance is the second factor on how strong gravity is, and it states that as distance increases, the force of gravity decreases. Given this diagram down here, you see that the masses of two objects are the same. The distance starts off closer, and then the objects are pulled further apart. So you would take the distance from the center of each of the masses, and what you would notice is that the force of gravity, or the pull between, or the pull on one object from the other, is going to weaken. The universal gravitation equation. It is denoted by the force equals the universal gravitational constant, G, with the mass of the first object and the mass of the second object in kilograms, all over d squared, which is the distance between the centers of objects 1 and 2. The universal gravitational constant is the strength of the gravity, and it is a given number that has already been calculated, and it will always be used whenever you are trying to solve for any of the other variables. The constant is 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared. Here is an example. Find the gravitational attraction which exists between a 50 kilogram girl and a 60 kilogram boy at a distance of 3.00 meters. We are going to use this equation down here, and we just plug in everything that we have. Here is our constant of G. 50 kilograms is the mass of the girl, and then the mass of the boy is 60 kilograms, all over the distance squared, which is 3 meters squared. After you solve for everything, there will be some values or some units of measurements that will cancel out. So you have kilograms squared over here, but you also have 2 kilograms, so those are going to cancel out. And you have 2.001, so when you multiply everything on the top part, it would come out to this, and that is Newton meters squared is what's left in the units of measurement. Underneath, when you square 3 meters, it becomes 9.00 meters squared. And the meters would cross out, and you would be left with newtons. And that is the unit of measurement for force. Your total should be, and if you check my math, should be 2.2 times 10 to the negative 8 newtons. Gravitational field or force field. It is an area of space that occupies the surrounding area of an object. It exists, but we don't really see lines. We represent them by lines, and what happens is the stronger force is closer to the object of greater mass. So there is going to be less space between the lines, as seen here. The further away that you get from Earth, it will create larger spaces between the lines to just show that it is a weaker force. It's just one way that we represent the strength of the gravitational field, also known as the force field. Going back to weight, we did learn this already, and we already know that weight is the gravitational force that pulls down on an object's mass. For example, if you were on Earth at a 9.81 meters per second squared, being the gravitational pull, If we were to take your mass and we multiply it by 9.81, you would have about 150 pounds, or half that in kilograms. If we were to take the same person who has the same mass, put him on the moon, he would experience a 1/6 of a difference in the gravity. Therefore, he will have less pull on his mass, and his weight would therefore be significantly less. If we take that same person with the same mass and put him on Jupiter, for example, where the gravity is 26.6 meters per second squared, the pull of the gravity of that planet would be greater than that of Earth, more than twice that. So therefore, he would feel like 406 pounds instead of just 150 on Earth. Now, if you've ever wondered how a scale works, it actually measures the upward force that is being pushed up against your body. Pretty cool. Remember what that's called? It's the normal force. Now, how is it possible to feel weightless? Let's look into this. Newton's second law of motion is something that we do need to look at in order to explain how it is that we can have changing masses depending on the gravity. We remember this, where force equals mass times acceleration. It shows the amount of force applied to an object based on its mass and its acceleration. We're going to be using this a lot in the next few slides. What is weightlessness? Weightlessness means, scientifically, when there are no forces that are supporting the body. So there are no forces that are acting upwards against our body, and therefore you actually don't weigh anything. For example, here's a man on a couch, and he is falling, and the couch is also falling, or the chair. Both the chair and the person are experiencing the same acceleration because they're falling and gravity is acting on both objects. So the chair is not able to exert pressure up on you, therefore the normal force is 0 newtons. The result is you feel weightless. Let's take a look. So here we have F equals ma, and we know that your normal force is going to be 0. So here we have F equals 0 newtons, and this is your mass times the pull of gravity. Because you have 0 over here, when you divide 9.81 meters per second squared into 0 newtons, you will get a mass of 0. So mathematically, it works out. Here are some other examples. You've probably experienced this. Hopefully, you've never experienced the first one. So if the elevator cable breaks, you would feel weightless. Going over the top of a roller coaster. This part right here, because both the roller coaster car and you are both falling, the roller coaster cannot push up on you. Therefore, you and the roller coaster car are weightless. Over here, an aircraft is going up into the air, and when it goes over the hump, it is actually weightless. So the other one is being in orbit. And when you're in orbit, you feel weightless. Let's look at how weight can change. Here's an elevator example. You have 4 different situations. One situation, you can actually have your normal weight. And this is where you are just standing in the elevator. The second picture over here is where you are going up in the elevator. And this is where you're going to experience a greater weight. When you're going down, you actually feel lighter. And when you are falling down, so let's say that the elevator broke, you would actually have no weight. So here's an example that you don't have to write down, but we are going to use this in the next few slides. So here is Otis, and his mass is 80 kilograms, and he is standing still, he's at rest on the elevator. Stage B, he is experiencing a 5.0 meters per second squared acceleration up. Down here, in stage C, we have a 5 meters per second squared acceleration down. And over here, it is accelerating at the rate of gravity. So we have 9.81 meters per second squared down. From this, we can calculate the normal force, which is the upward push up on Otis. And given that we find the normal force, we should be able to figure out what he weighs at that moment in time. Let's do the math. Okay, let's take a look at Otis when he is standing still. So there are some things that we know. We know that when he is not moving, that the acceleration is 0. He's not going anywhere. When the acceleration is 0 and the person or the object is at rest, we also know that the normal force equals that of the weight of the object. So in this case, the normal force equals the force of the gravity or the weight of Otis. This is static equilibrium. The first step that we want to do is change the kilograms into newtons. So we want to find the weight. And when we do that, we find W equals mg. So let's plug everything in and find Otis's mass, or his weight, and that is 80 kilograms times 9.8 meters per second squared, and that gives us a total of 785 newtons. Now that we have this, we can continue on to the second step. We want to solve for the net force. So in order to do that, we have to remember that force equals mass times acceleration. So let's figure this out. When we plug this in, we have 80 kilograms, which is the mass of Otis, times the acceleration, which is 0. So we actually have a net force of 0, which we already knew because Otis is just sitting there or standing there in the elevator. Next is that we want to actually try to find the normal force. So we know that the net force is pretty much both arrows either subtracted or added depending on whether or not they're going in the same direction or in opposite directions. In this case, we know that the net force is the normal force minus that of the gravity. So here I have gravity minus the normal force. Because I want to solve for the normal force, I just have to get it all by itself, so I move things around, and I should then get an equation that looks like this. The normal force equals the force of gravity minus the net force. When I plug this all in, and I already know that the gravitational force is the weight of Otis, 785 newtons, minus the net force, which is 0 newtons, gives me a total of 785 newtons, which goes completely with our theory because it should equal the normal force and the gravitational force should equal each other because Otis is at rest. Therefore, his weight stays the same. Here is Otis in stage B, where he is experiencing an acceleration of 5 meters per second upwards. His mass, or his weight, is still the same at 785 newtons. If you're wondering why this is negative, it is because, remember whenever we had falling objects, it was given a positive 9.81 meters per second going downwards. Because I'm going in the opposite direction of what gravity would be, pulling on an object, I am going to make this value negative. I already know the weight, so we don't have to find the weight again. Step 1 then would then be to solve for the normal force. We would use F equals ma, plug everything in, and you would get a total of negative 400 newtons going up. When we find the normal force, we just have to subtract, so I have 785 minus 400 newtons up. So when you have a negative and a minusing a negative, you would get a positive 400 newtons up. So you would add the two figures and you get a total of 1,185 newtons. The new weight would then be F equals ma, and your total would then be 237 kilograms. You might be wondering why I didn't use a negative here. However, I did use a negative throughout all of the other calculations. The reason is because we can't have a negative weight. Otis has to weigh something. He can either weigh 0, but he can't weigh anything negative. So therefore, I just took the force equals mass times the acceleration in the positive form. Either that or you could just take the absolute value at the end. So Otis's weight is going to be 237 kilograms when he is accelerating upwards at 5 meters per second squared. Go ahead and try to solve for this. Now Otis is going down 5 meters per second squared. His weight is still the same, and we need to solve for what the normal force is so we can figure out what his new weight is. Step 1 is to solve for the normal force. When we plug everything in, we get a total of 400 newtons going down. Then we need to find the normal force, which is the gravity minus the net force. So when we do that, we get a total of 385 newtons. Plugging this back in into F equals ma, his new weight is now 77 kilograms. Stage D, with Otis now in a free fall in the elevator. Go ahead and try to solve this, and let's see if we come up with the same answer. Solving for the normal force, we know that F equals ma. Plugging everything in, we get a total of 785 newtons down. Finding the normal force, it is the gravity minus the net force. When we plug everything in, we get a total of 0 newtons. Therefore, his new weight is nothing. He weighs nothing. All right, so just be ready to use this in class next, and have a great day.